So you have never taken the CAE class with anybody, right? CAE computer aided engineering? No? Okay, because we had some change in our curriculum and CAE was deleted from the curriculum. Okay, if this is the case, I'm going to talk about this one more depth. So the computer aided engineering talks about the elasticity. That's the reason because there's some overlapping between the CAE and machine design. That's the reason. So finally, the CAE was deleted. But now I'm going to talk about the stress. You have learned the mechanics of solids, right? Have you? Yeah. So in that course, have you learned the stress and strain? Yeah. Yeah. Okay. So I'm going to go through these slides. If you have questions, feel free to ask me. I know because you have never taken CAE, so there might be some guide, and there might not. But let me know, okay? So this is the stress. The stress. Let me tell you, stress is the most important concept in the solid mechanics. So what is the stress? The stress here is this is a diagram for this ABC. So suppose we have this is a problem domain, and we have external forces here. If we use imaginary plane to card this is the problem domain, and we just isolate this half. And then we artificially establish XYZ Cartesian coordinates. And then for any generic point, and we have suppose we have a delta F, okay, the force is delta F. So this area is delta A. So this is, we call this one the internal forces. Why? Because we just use imaginary plane to cut this is the whole problem domain into half. So this is, we call this the internal force. So these internal forces try to balance the external forces on this side. So make sure, so this is the problem domain does not translate and does not rotate. That means I want this guy to be in a state of equilibrium. So on how to get this one, how to get this here, okay, we can just zoom in and we just focus on here. So we just re-establish a new XYZ coordinate system. So here is this is area. So this is my force, and I have three forces. This is X, Y, and Z. So keep in mind. So this is the XYZ coordinate system is artificially imposed. So different people might have different preference, but without lots of generality, I just use this one as X, this one, and Z. By following this right-hand rule, X, Y, Z. So this is the point. So this area, this is the three forces. So I can have I can write this is sigma X. This is stress. Stress can be interpreted as the force per unit volume, per unit area. So this is delta Fx over delta A. This one is in X direction. So I just use the subscript X to denote. So this is in X direction. Stress is X direction. So we just take a limit as delta A goes to 0. And so we have dFx dA. So this is the derivative of Fx with respect to area. Questions? So also, similarly for these two sides, so this is a normal side. This is normal direction. Normal direction. So this is a imaginary plane. So also we have other the shear direction. So this y direction and this is z direction. They are perpendicular. They are parallel to this imaginary plane. So that we use a tau and tau xy. Tau xy means that is a take the limit of delta Fy over the same area, delta A. So similarly for here, that's on this tau xz. So we have for the normal stress, we call this normal stress. Normal means that the direction is perpendicular and to this is the plane of interest. So this is a normal stress, and these two guys are called shear stress. Shear stress means that these two guys' direction and they are parallel to the plane. Right? Questions? No questions? No questions. So, and for the shear stress, and we usually have two subscripts. So these two subscripts, they have different meanings. So first subscript is used to denote the plane, right? So the normal to the plane. I want you guys to write down because I don't know whether you have learned this in the mechanical solid or not. So this the first subscript denotes the direction of the normal direction of the plane you are interested in. So for our case, the normal direction of my plane is x, right? So this is x. Second subscript, y here is used to denote the direction of your stress, the actual direction of the stress. For here, this is in the y direction. So this tau xz is the same thing. X means that I'm on this plane, so this guy's normal is in x direction. Now this actual direction of the y of this shear is the z direction. Right? So this is just one plane. You can just imagine if we have a plane which if we cut it this way, if we can use a horizontal plane to cut it, so this will be my y, this is my x. So we can have a normal stress sigma y, and we can have the shear stress is tau yx or tau yz. So one more time. So the first subscript is used to denote the direction of normal direction of the plane you are interested in. A second subscript denotes the direction of your stress, actual stress. Questions? These are fundamentals, correct? So we have the equilibrium equation, and based on Newton's law about this equilibrium equation, we have and this is the three this fx and sigma fy and sigma fz, and so they are equal to 0. So these are three equations, and I used to guarantee that this problem domain does not contain in x, y, z direction. And so we also have sigma mx equals sigma my equals sigma mz. So that means the resultant moment for all these three axes, they are equal to 0. So these three equations, they are used to make sure the shear stress, they are symmetric. Right? So that means until we use these three equations, we can get the tau xy equals tau yx and tau yz equals tau zy, and this is tau xz equals tau and zx. So we get these three symmetric the tau by using these three equations. And from this equation, so these are three force balance equation, we get this. Right? So this is a force balance equation. They are written in terms of stress instead of force. So this is what we have learned either in the high school or either this is early lower either freshman or the senior junior sophomore. I'm sorry. Now, if we want to use the stress component and to express the equilibrium equations, we use these other equations. Right? You can see sigma. We totally have the 6. We told because the symmetry of this shear stress, we have 6 independent stress components, and they are this is sigma x and sigma. We use the shear. Okay, so this is sigma and xy and sigma xz. So this is equals tau xz. Okay. So sometimes we use the sigma, and if you can see if the two subscripts are different, that means this guy is a shear stress. Okay. So I prefer to use this one because these three equations can be written using one simple equation. So we have sigma xy because the symmetric, this guy equals this guy, and sigma yy and sigma yz. And supposedly, originally this way should be x, yx. Okay? It's yx, and then this one. This is a zx, so this is zy, this is a sigma zd. So this is my sigma, the stress tensor. So this is, we have three. It looks like it's three, but as I said, so these guys, they are symmetric. This one equals this one, this one equals this, this one equals this. So finally, I can just change this onto xy. So this is xc. So this is the y. So that means 1, 2, 3, 4, 5, 6. So these 6 space components, they are independent. But these 3, and they are because they are equal to sigma xy and sigma yz and sigma xz. Questions regarding this one? So sometimes I write sigma, I use the sigma for all stress components. Don't panic, okay? As long as I use different subscripts, that means the shear. So these Fx, Fy, and Fz, they are the body force. Fx, Fy, and Fz. Fy, Fz, they are body force. They are body force. The body force means this is a Newton, and this is the force per unit volume. Force per unit volume. Per unit volume. Force per unit volume. So use 3 directions: x, y, and z. Questions regarding this one? No question? No question, then move on to the next one. So with the kinematic equations, that is the last slide shows is the equilibrium equation. So now then we talk about the kinematic equation. The kinematic equations this relate the displacement to strain, right? The U is the displacement, and UVW, the UVW here, UVW, and they are the displacement in 3 directions. So this is in x direction, so this is in y, and this is in z direction. And so how the displacements are related to the strain, and we have here du dx equals epsilon x is a normal strain in x direction, epsilon y is normal strain in y direction, but this is a v. V is the displacement in second direction in y direction with respect to y. So this is epsilon z is a dw over dz. Right? And then we have this is the gamma. The gamma is the engineering shear strain. So we have shear strain here. So this here. So this is the epsilon ij. If I and j they are different, and so this is a shear strain. And shear strain equals half of this engineering shear strain. And we have strain shear, tensor shear strain, and it's epsilon ij, and also engineering shear strain. The gamma ij. So gamma ij equals double epsilon ij. Right. So these equations, so we can use this one. So this is more general. Epsilon ij equals this. This ij either this I can be equal to j can be different. These two guys can be different. So this is dui. We can say dui dxj duj and dxi. This is more. So for here, I would let's say this is x. Okay. So this is x1 means x. So x2 means y, and x3 means z. If you are not okay with this one, I'm still fine. So you can just memorize this one. Okay. So this one is the Einstein notation or the initial notation. I will guess ever heard Einstein notation, so also called initial. Or called Einstein notation. So initial notation or Einstein notation, you know Einstein, right? Einstein notation. And so this is, we use the sigma for all the stress. And we use this convention. And we only use X. We don't use YZ. We only use X. But we have XY and X2, X3. So X1 corresponds to our X, X2 corresponds to our Y, X3 corresponds to our Z. So we only use sigma, we do not use shear. We do not use tau. Only use tau. Only use tau. So this is Einstein notation. So if you are okay with this one, so this one equation can accommodate all these 6 equations if you use the Einstein notation. Questions so far? No question? So if we have the displacement distribution functions, by using these 6 equations, we can get the string components. Now, and then this talk about this Hooke's law. You have learned the Hooke's law, right? Hooke's law. Hooke's law, that is the 1D Hooke's law. 1D the Hooke's law. 1D Hooke's law says that sigma equals Young's modulus multiplied by Epsilon, right? You still remember, guys? So this is 1D, and this is Hooke's law, and relates the strain and to the stress. And for the 3D, and how can we relate the stress components and strain components? And we have 2 equations. Okay? So these 2 equations, they are based on the same thing, but which equation you use depends upon what you know and what you are solving for. And for example, for this one, if you know the strain components and you want to calculate the corresponding stress components, and you use this equation. Okay? And however, if the stress components they are known, and you want to calculate the strain components, and you are supposed to use this equation. Okay? However, some students say, I'm good at the mathematics. That's still okay. You can use this one, but you need to do the inverse by yourself. Okay? Questions so far? So one more time. So which equation you should use depending upon what are known values and what are unknown values. If you know the strain components and you want to calculate the stress component using this equation, and on the contrary, if you know the stress components and you want to calculate the strain component, and you are supposed to use this equation. So Young's modulus E, the new here is Poisson's ratio, right? Young's modulus A, new is the Poisson's ratio. So be very, very careful. If you have a factor 1/2 for these 3, the entries, so you should have 2 here. Right? So if you don't want this 1/2 these factors here, and you need to get rid of these 2 or these 3 guys to be consistent. The same thing for here. 2, 2, 2. If you don't want these 2, 2, 2, you just get rid of these 2, 2. Questions so far? No question. That's to you can see the stress. We talk about stress, we talk about strain, and then we relate the stress and strain. And then we talk about so this is a case. Normal stress for beam in bending. So this is a pure bending. Suppose we have a beam. This is a beam, and we just bend it, and we only have this bending moment. So when we normal stress, if we have pure bending, and usually we have this is the normal stress. If we cross this, if this is our x, if we cut it this way, which is perpendicular to x, and we will have the normal stress. Normal stress, a straight beam in positive bending. So x-axis, x-axis is a neutral axis. What is a neutral axis? X-axis, neutral axis means that if you bend it, Let's just suppose, okay, let's see, suppose we have infinite number of fibers from this end to this end. These fibers, they are arranged parallel to one another. So neutral axis means that on this axis, if you bend it, the length of the fiber does not change. It's neutral axis. You understand? So this XZ complaint, XZ, say X and Z. So this plane is neutral plane. Neutral plane means that all these fibers from there to here, and on this plane, as you bend it, the length remains the same. So neutral axis is coincided with the centroidal axis of the cross section. So what is the centroidal axis? Centroidal is the mass, okay? The mass center of the mass. Centroidal is the center of the mass. Why this statement is true? Because, so this is a rectangular shape. So this cross section is a rectangular shape. If you change, if this is an irregular shape, so this statement is wrong. Okay? So from this slide, you know that if you have pure bending, and we will have normal stress, and we have neutral axis. What is a neutral axis? And also, if this is a cross-sectional area is a regular one means that this symmetric, right? Symmetric in about this axis, then the neutral axis and the centroidal axis, they are the same. They are identical. Questions? Over? No question? No question. Next one. Normal stress is a normal stress here. So here, so this is our neutral axis. You can see neutral axis after you bend it. So if suppose we have a fiber from here to here, and these fibers length remains the same. So how can we calculate the bending stress? And so we did the sigma x equals the bending moment divided by I. I is the area of moment of inertia, which is closely related to the cross-sectional area, cross-sectional shape. The I is the area moment of inertia. It calls second area moment of and so this one I equals y squared dA. So to the integral. That is about the cross section. So you can see. So this I has nothing to do with the material. Has nothing to do with the loading. It has relationship only with the geometry. So I is a geometric parameter. What? Questions? So for this one, because this fiber does not change the length, that means strain equals 0. That means sigma equals 0. You guys agree? Because the length does not change, that means no strain. Because no strain, use the Hooke's law and no stress. This stress is supposed to be 0. However, as the point, the moves from this is a neutral axis and to the outside. So this stress is changing proportionally. So it's increasing. And so this one can be explained using this equation also. You can see I is constant as long as we have the uniform the cross-sectional area throughout this beam. And so we only have this sigma is only dependent upon y. And y is the distance between the point of interest and to the neutral axis. This is 1. Y is the distance between the point of interest and the neutral axis. If you bend it this way, okay, if you bend it this way, so this will compressing the stress. So here is the tensile stress. You can see neutral axis and the centroidal axis, they are identical for these special readings. Questions? No question? Move on to the next one. So maximum bending stress. So maximum bending stress, we have that equation sigma equals negative m y divided by I. And then what is the maximum? Then maximum means that and when y equals the maximum. Y equals maximum. So here, right? So this is C. So this is distance, C, will change the C. So my M maximum can be written as M, and this is divided by capital Z. The capital Z is I divided by C. And we introduced another concept, I. This is Z. Z equals I remove the inertia. C is the distance between the outer layer and to the neutral axis. So this is just one plane. One. This is we will have one single. This is the moment about one plane. What is the two plane bending? Two plane bending means that we have bending in two different planes. So, for example, in both XY and XZ plane, we have bending. So, how to do that? Because the bending moment and they are vector, right? Do you guys agree? They are vector. So sigma x. So just as this one. So two plane bending means that this is my beam. I bend it this way. So this is one bending, and then I bend it this way. What? So however, for this one, I have a sigma, a normal stress in x direction. And for this bending, I also have the normal stress also in x, right? So that means my two sigma and they are in the same direction, in x direction. That means I can just put them together algebraically, even though mz and my and they are vectors. Right? They are vectors, but I still can put them together. The reason is that the resultant stress, normal stress, they are in the same direction for these two cases. So for solid circular cross section, the maximum bending moment is this. Okay, so for circular cross section, how can we simplify this equation to here? And for circular cross section, Iz equals Iy because the circle is symmetric for any plane that is passing the center. You guys agree? That's the reason. Because Iz equals Iy if I have a circular cross section. So that Iz equals Iy. I equals id power 4 divided by 64. So this is I. C equals the radius of the cross section, which equals 2d. So I want you guys to memorize this one, okay? For the circular cross section, the area moment inertia equals pi d power 4 divided by 64. And the J is the polar moment inertia equals 2I. Questions? No question? You want the next one? So look at the shear. The shear stress for beam in bending. So suppose we have this beam and we have this omega x. Omega x is uniformly distributed force, and we will have suppose we have this infinitesimally small is a distance dx, this is x, and so we have v here. V is a transverse shear, and this is the bending moment, right? So this is a bending moment, and so we can see here this is sigma x. This is normal stress in x direction. It equals minus my divided by I. And also, so you have, this is on one side, on another side, you have dmy. So because the my is changing, so this is m plus dm. So here, so this is a balanced. This is called shear stress. Okay, the shear stress equals V, and V is the transverse shear divided by IB. The y from yi to c is y dx, and yi. So this is from yi and to c, from here to here. We just want to integrate. So this is tau, how to calculate tau. So this tau b dx is used to balance, and this is m, this is a bending moment. So on this side, so tau multiplied by b is the width, and dx and they are we multiply them together. So this one is used to balance this one. So finally, we can get this tau here. So this is F. So this F can be written as is a dmy also. Dm means the change of the moment from this side, left hand side to the right hand side. So I'll give you the equation here. So this is the tau. We use this transverse shear stress, and it's a tau. We use a V divided by multiplied by Q divided by IB, and B is the width of the beam. B is the width of the beam. The transverse shear stress is always accompanied with a bending stress. The transverse shear stress is always accompanied with bending stress. So at the very beginning, I talked about the pure bending process. The pure bending actually, in reality, it does not exist. That is just idealized case for illustration. So transverse shear stress in a rectangular beam, for a rectangular beam, and this is the tau. How can I calculate? This is my Q, okay? This continued from the last slide. This is Q. So this is how to do it. I want you guys to take a look. It's a tau, but just a substitute Q inside. So this is the final equation we should have. It's a tau. So we need to calculate the V, the transverse shear. And then we use this equation to calculate the tau. Questions? Okay, so for different this is a machine design course, and we will select. We will design something, and we will select the stock, the material piece from manufacturers, and you will have different beam shape. And this is a rectangular, circular, and so this is a hollow thin wall, and so this is I-beam shape. And we need to use some equations to calculate before we can select the appropriate components. And for this beam shape, and tau maximum can be calculated using this equation. V is a transverse shear. So for the circular, and 4 times V divided by 3A. For this, the hollow one, we have this equation. And for this structure beam, I-beam, we have this equation. So please keep in mind. And so you can just, you don't need to memorize this one. So if there's a need, you come back to just check these equations. All right? Questions so far? No question? Let's move on to the next one. So our goal is to select the appropriate products. So significance of transverse shears compared to bending. So for example, this is the cantilever beam. We have a cantilever beam, and suppose it has rectangular cross section. So maximum shear stress, including bending stress in the x direction, in the center line direction, and the transverse shear stress is perpendicular. So this is tau maximum equals this, because the normal stress and shear stress, they are perpendicular. So this equation, tau maximum equals half of sigma plus tau squared. So this one, okay, and so this one is based upon this is the Vomicis criteria, Vomicis failure criteria. You can get this sigma maximum. So this one is based on the transverse. No, I'm sorry. So this is the Pythagorean theorem. So we have a sigma and we have a tau. They are perpendicular. So we can calculate this tau, okay, and calculate this tau using Pythagorean theorem, and then we compare. So this one with the failure criteria, with the failure. So how to calculate the sigma? How to calculate sigma? And we just plug in. How to calculate tau? We just plug in. You can see. So we can use this y over c, the ratio. different ratio, we have different curves. That means this is L divided by H. So this is tau maximum. So we want the tau to be as low as possible. Just to stay away from the failure criteria, failure point. Questions, guys? Are you following me? Okay, this one you don't need to memorize. And what I want you guys to memorize is this. These are fundamentals. All this is the detailed equations, and you can just come back and to take a look. But what I want you to memorize is equilibrium equations, kinematic equations, and this is the generalized Hooke's law. That is the fundamentals of the fundamentals. Right? For these equations, no, you don't need to memorize. Just come back to look at the slide. I cannot memorize. My memory is poor. I cannot memorize this. But I can use it. Okay? Whenever I need, there's a need, I just come back and I know which equation I should use. So critical stress elements, largest, this one will always be either due to bending on the outer surface or due to transverse shear as the neutral axis where the bending is zero. The transition happens at some critical point of this L divided by H, valid for any cross section that does not increase in width further away from the neutral axis. Then we talk about bending. Now we talk about the torsion. So we are going to talk about different loading conditions, bending and then torsion. So you can see this is the torsion. So we have this is the beam, and we have a beam, and then we twist it. And so twist it, how to twist it? And we use the right-hand rule. So this twisting moment is a vector. So we use this vector is going this way. So that means I'm going to twist. This is my torque. This torque is twisting torque is going to twist this beam this way. Okay. So this is the axis. And how to do that? This is a bar, the angle of the twister. So this one is calculated as this tweak. This torque you apply. L is the length of the beam, and G is the shear modulus, and the J. And what is J, guys? I forgot. Okay. Yeah, polar moment of inertia. Now this time is a polar moment of inertia. This is for the solid runner bar. We have this one. This equation is only for it's a solid runner bar. So this is as long as it is the cross section is consistent, is uniform throughout this along this axis. Questions? No question? Then this is a theta. Okay. If we get we have a load, torque. And then we know how to calculate the angle, the twisting angle. And then how can we calculate the shear stress tau? And so this guy equals the torque multiplied by rho divided by J. And rho is the distance between the point of interest to the center of this cross section. What? Once again, this rho is a distance between the point of interest and to the center. So here, suppose this is the point of interest. I want to see what is the shear stress at this point, and then the rho is from here to here. You can see the rho is not constant for all these cross section area, all the points on this cross section area, and the tau is changing. The maximum torsion shear stress is at the outer surface. We know the rho for this circular bar, at which point the rho is maximum is on the outer surface, and which equals the radius of the cross section. So this circular bar is very straightforward. However, for torsional shear in the rectangular section is known. Okay? This is why? Because this is not cost. If you have a square, and this square is not symmetric along all of these the planes that is passing this central axis. Do you agree? So as a result, it is more complicated. Shear stress does not vary linearly with radial distance from rectangular cross section. Shear stress is still zero at the corners. The maximum shear stress is at the mid of the longest side. For rectangular, the shape B is the base and C is height, and B is the longest of the side. So this tau can be calculated using this one. Can be approximated using this. And theta, twisting angle, can be approximated using this one. So how to calculate the ratio of B to C? This is alpha and beta. And it depends on this, right? So based on B and C, the ratio of B and C, you have different alpha and different beta. So this dot means approximation. It's not analytical, not exact. Questions? Question? And no question, we move on to the next slide. So we talk about power. And the power, speed, and torque. So this is usually commonly used concepts when we design something. Design a machine, you need to know the power you want this machine to output, the speed, the rotating speed of the shaft or gear, the torque, how much torque you want to transfer. So power equals the torque times speed. And the H, we use H. H is equals the product of the torque, the torque multiplied by the omega. Omega is the rotational speed. The power, the watts, the torque, this is Newton meter. The omega, angular velocity, which is radial second. So these three units, they are international standard units. Watts, Newton meter, and radian second. However, sometimes the horsepower, we use horsepower for the power. So sometimes we use this. Okay, so this is a conversion with the speed in RPM. So in RPM, so this is the radian per second. And however, if we use the speed in RPM, so we have this conversion. Where here H is a still power, but N here is revolution per minute, and you need to use this equation. Right? And which equation is correct? And both of them are correct. One to use this one, one to use that one, are dependent upon what kind of units you are using. Right? You understand, guys? Yeah, as I said, if we use this P, if the H power we use the horsepower, and we have another equation. So now this is horsepower. Okay, in the US customer units. So H with units built into this H equals F. So VT velocity feet per minute. Okay. F is a pound force. N is a revolution per minute. T is a torque, pound force per inch. And then the H will be the horsepower. 1 horsepower equals 735. And this is the loss. Right? So if we use the US customary units, and you are supposed to use this one. As I said, which equations they are correct? All of them are correct. And which one to use dependent upon which units, which set of units you are using. Okay? So here is an example. This example, and I want you guys to take a look, right? To take a look at this example, and so this Friday, and after we come back, I'm going to talk about this one a little bit. So then I want to talk about this and close the symbol tools. So this is kind of new, so I want to emphasize more. So this is if we have a very simple tools, and we have the different, I would have new equations that can excite you guys. So suppose, so this is thickness if the T is much smaller than the tube radius of this, if the T is much smaller than the R, and the product of the shear stress times what the thickness is constant.